A Hasse diagram is a graph that's used to depict a partial order on a finite set. And notice I said, do we need these ones off too?
I feel like please.
Where is this? Okay. Okay. So notice this says graph and it does not say digraph. Okay, so it's not a digraph. Okay, so the edges aren't directed. So a directed edge like has an arrow on one end and not on the other end. So this graph doesn't have any little arrows on the edges, so they're not directed. Okay, so they're just even taking the arrows off simplifies the diagram itself. So it's a graph, not a digraph, that's used to depict a partial order. Okay, and we know that it's a partial order, and so there's a lot of information that is implied by the diagram because we know it's only used for partial orders. Okay, and so here are kind of the rules. So this Hasse diagram shows the precedence relationships by placing elements that are greater towards the top. So remember we talked about maximal elements. So the ones that are greater in terms of the relation, those are going to go towards the top. And the ones that are smaller in terms of the relationship are going to go towards the bottom. Okay. And then we only include the bare minimum number of edges to make the relationships clear. So, for example, okay, we don't have no self loops, for example. So we're going to remove all the self loops. We know it's a partial order. Every partial order is reflexive. We know the self loops are there. There's no reason to clutter up our diagram with those because we know they're there because it's a partial order. We're going to take those away. And then if we have something like this where we have A is related to B and B is related to C, well, because it's transitive, we get this extra edge in here. And we'll take all of those out. Okay. So all of these ones that are in there because of transitivity, we'll take the extra ones out. If I know that A is related to B and B is related to C, well, it's a partial order. It's transitive. A has to be related to C. And I'll get that idea when I see this path that goes from A to C in there. Okay, so I'm going to take out, okay, so take out these transitive edges, I'll call them. Okay. So all of those will be gone, and the diagram those will be implied by the diagram. Okay. So we'll take out the self loops, we'll take out all these extra transitive edges that can be implied by what's already in the rest of the diagram. So the rules for drawing this Hasse diagram are that, okay, so we have two elements, x and y. They're not the same. Okay, so if x is related to y in this partial order, okay, and notice when we talk about something being smaller or greater, I know this can be, it doesn't necessarily mean less than in number. Like what we're saying, like this one is smaller, x is smaller, and y is greater in terms of the relationship. Okay, so because x is smaller in terms of whatever relationship we're talking about, it's going to appear lower in the diagram, and because y is greater, it's going to appear higher. Okay, so, and then that lower higher is that's gonna give us additional information by knowing, it'll help us know these relationships. Okay, and then also, this is where we get rid of the transitive edges. So if I have, that x is related to y, and there isn't any z, such that I have this kind of middleman where x is related to z and z is related to y, then and only then will I draw an edge between x and y, because there isn't already a transitive relationship applied, so I have to put that one in there. But if there were some kind of z in there, then I'm already going to get this x related to y relationship implied, and I'm not going to put the edge in. Okay, so this rule right here is about not putting those transitive edges in. Okay. So let's look at the previous two examples that we looked at. So the Hasse diagram for this mess right here. Okay, so that's going to be this one. So it's the same thing. We've already done this exact one. Okay. And then we're going to look at the Hasse diagram for this one, and that's on the previous page. So we drew the digraph back here, but we're going to look at what the Hasse diagram for that one would be. Okay. So, first of all, the Hasse diagram here. So let's go back to our previous one and look at, so we know that anything, that's smaller than another thing has to appear lower. So if we can find any minimal elements, those will be at the bottom of our Hasse diagram. So those are important to find. So if we go back to the example that we did back here, our minimal element was the empty set. So in our Hasse diagram, that is going to go at the very bottom because there's nothing below that. There's nothing less than that. So we're going to put the minimal element at the bottom. Okay, so this is, I'm going to put this one over here. So I'm going to have my empty set down there. Okay. And then I'm going to have an edge to whatever that's related to, as long as they're, and then except for these, something that can be implied by a transitive relationship. Okay, so if I go like from here, I had this relationship here where the empty set was related to the set containing 0. Okay, so then we would ask ourselves, well, the only way that I would put that in my Hasse diagram is if there wasn't some other set in between these two that allowed me to get this relationship by transitivity. Okay, and notice there isn't. There's nothing in between here and here where I can say, oh, well, the empty set is related to, this, and that's related to this one, and so it would go, no, because all the arrows go in this direction on this one. So there's nothing sort of like in between the empty set and the set containing 0. So I'd have to put that edge there. So I'm going to include this one. And notice it's going to go higher in my diagram, okay? So anything that's greater is going to go up higher in the diagram. So I'm going to put the set containing 0 up there, and I'll put an edge between them. Okay, so I'll have that one. And sort of for all of these ones, I have a similar situation. So there's nothing in between the empty set and the set containing 1 that implies this relationship. This is kind of like the next smallest set there is. There's nothing in between there. So that's also going to go above the empty set. Okay. The question is, should it also be above the 0, the set containing 0? Well, notice these are not related. These are incomparable elements. There's no line from 0 to the set containing 0 to the set containing 1. There's no line or relationship from the set containing 1 to the set containing 0. These are incomparable, so these can go on the same level in the Hasse diagram, just like they kind of were in this same level on my digraph as well. So I'll put that one there. And then the set containing just 2 is in a similar situation. They're all okay. So far, that's not that much different than the digraph. I just didn't put any arrows on it. But what we do next, you'll see there's lots of differences. All right, so the next set we want to think about is this one, a set containing 0 and 1. Okay. And so that, sorry, what? Okay. Yes, we're going to see the transitives. So the set containing 0 and 1. Okay, now that, notice there is a directed edge here from the set containing 0 to the set containing 0 and 1. So this set containing 0, 1 is going to have to appear higher in the diagram than the set containing just 0. Okay. So we're going to have to put that one higher. I'm going to put that one up here. Okay. And now in this diagram, notice I have this one, this edge here, okay, from the empty set, because the empty set is a subset of the set containing 0, 1. But in my Hasse diagram, the only way I'm going to put an edge is if there isn't like anything in between there that I could get by transitivity. So if I put this edge in here, okay, well, there does exist a z, this one, where I have empty set is related to the set containing 0. The set containing 0 is related to the set containing 0 and 1. So by transitivity, the empty set is related to the set containing 0 and 1. Okay, because I can get that relationship by transitivity from what I've already listed here, I'm not going to put that edge in. Okay, I'm just going to leave that one out. And basically, if I can find an upward path, so here, if I can like follow an upward path to it, I know those are related because of transitivity. Okay. So I've got that 0, 1. Let's put in the 0, 2. Okay. So 0 is a subset of that one, so I'll put in this edge. And then I'm not going to put in an edge from the empty set to that one because I have this upward path there, and so by transitivity I know that relationship exists. But I do need to put this one in. Okay, no arrow, sorry. Okay, and once again, I know that this relationship exists because of that transitivity. Okay, oh, and I should have put this one in. Okay, so 1 is a subset of 0, 1, so that one should be there as well. Okay, this one is not a subset of 0, 2. There's not going to be any edge there. The other subset of size 2 is the one that has 1, 2 in it. That has to be above the 2. It has to be above the 1 because both of those are subsets. So we'll have both of those edges in there. It's going to look like a cube when we're done. Yep. And then there's one more at the end that has 0, 1, and 2. Okay. And so this is a subset, this is a subset, and this is a subset. Yeah, if you look at it right, it looks like a cube, doesn't it? I mean, you've got the little sets on the little vertices of that cube. Okay. But this, is where, if you compare these two, they give all the same information, but this one is so much easier to look at and digest and understand what it means because it doesn't have all those extra transitive edges, it doesn't have all those extra loops, it's just not as busy. Conveys all the same information, it's just a lot easier to look at it. Also, we can see that the minimal elements are always going to be at the bottom with nothing under them. The maximal elements will always be at the top with nothing above them. Okay. So that is the Hasse diagram for that subset. Okay. And interesting, you'll get these, you always get some kind of a cube or a hypercube when you do the subset. So if you ever were to go and study these more, it's all these cool things happen. We don't have time for that today. Maybe some future theory class you'll get into that. All right, and then, so let's do this one. So this one was on page 18. Okay. See how much of that we can get on here. Okay, and so this one, we'd like to put this into a Hasse diagram. Again, there are lots of these, all these busy edges and loops, and we'll see that the Hasse diagram just minimizes the amount of information, so we capture all of this, but it will be a minimal amount of information. Okay, so once again, it's helpful to know what the minimal element is because that's the thing that has to go at the bottom in the Hasse diagram. So we figured out that 2 was the minimal element. So in my Hasse diagram, I would put 2 at the bottom. And then 2, yeah, it's hard to get them both on here and see everything. So yeah, I'm just going to. Okay. All right. We got the information we needed about the minimal. That's all we needed. All right, so the 2 is going to go at the bottom. That was minimal. Okay. And then 2, remember this was the divides relationship, 2 divides 4. So 2 has to appear lower than 4. So 4 is going to go above it. We're not going to put any self loops on 2. That's implied. I know it's reflexive. There's no reason to put that in there. Okay. And then the next number we have to consider is 8. Okay. Well, 4 divides 8, so 8 has to appear above 4. So 8's going to have to go up here above 4. 4 divides 8. It's related to it. So I'll put that edge in. But I'm not going to put the edge from 2 to 8. That's implied because I have this upward path from 2 to 8. So by transitivity, I know that 2 and 8 are related. Then I need to consider 16. Well, 8 divides 16, so 16 has to appear above 8. So I'll put 16 up here. There's a relationship there. And now there's an upward path from 2 to 16. So I know 2 and 16 are related. There's an upward path from 4 to 16. I know 4 and 16 are related. All of that by transitivity. I'm not going to put any of those edges in because it's all implied in the diagram. Okay, and finally, I've got the 32. Well, 16 divides 32, so 32 has to appear above the 16. Okay. And then I have all these upward paths, so I see that everything under the 32 is also related to it. Okay. And so here's where I see that I've got a total order, because I just have all of my elements in my set in one long string. So here you can easily see this is a total order because everything is lined up in a string in my Hasse diagram. Here I don't have a total order because I've got these things. So for instance, there is no upward path between 0 and 2. If I went up, I'd have to go back down to get to 2. So I can't ever go down if I want things to be related. Only up. Okay. So all the upward paths show the relationships, but you can never go down to get a relationship. Okay, so this one you can easily see it's not a total order. It's not just one long string. This one you can easily see that it is a total order. Okay. So the Hasse diagrams are nice and concise. And so it's a lot easier to answer questions about like finding minimal and maximal elements or seeing if it's a total order. So let's look at these different Hasse diagrams. Okay, so in this one, we want to find the minimal and maximal elements, and there might be more than one. There might be more than one. So just remember, a minimal element is an element where there's nothing that's less than it, whatever less than means in the relationship that we've defined. Okay, so basically in a Hasse diagram, there's nothing under it. Okay, so for this one, how many things do we have at the lowest level where there's nothing like under or below it? D. D is the only one. Yeah, so we have one minimal element, that one's D. And then how about the maximal element would be something where there's nothing above it. And there's only one of those, and it's what? It's A. Sorry. Okay. Now if we go over here, okay, how many minimal elements do we have in post set B? There's 2 of them, and they are E and F. Okay, so these are both on the lowest level, and there's nothing below them, so these are both minimal. And then what are our maximal elements? A and B. Okay, so for both A and B, there's nothing above them, so those are maximal. And then for post set C, this one's a little tricky. How many minimals do we have?
3.
There's actually 3. Good. And what are they? C, H, and D. So here's C, H, and D. So all of those are minimal. Okay. And there's really no reason that we couldn't have drawn C down here and just put a really long edge, or D down here and put a... It's mostly just, you know, because the placement of these, and they don't want the edges to overlap or something. So okay. You just look for something where there's nothing below it. So C has nothing below it. D has nothing below it, even though it's not lined up here at the bottom. Okay, and then how about the maximal elements for this one? A and F. Okay, and then the minimal ones over here are E and D. And then the maximal elements are A and B. So are any of these total orders? So that's the big question. Like, it's pretty clear that none of these are total orders, but D is the question. Is that a total order? So in a total order, every two pairs of elements have to be comparable. So in this, do we have any incomparable elements? Yes, we do. So this is not a total order because we have incomparable elements. So like A and D aren't comparable. A and B aren't comparable. C and B aren't comparable. We have lots of pairs of elements that are incomparable. So, because, if I had just this part of it, that would be a total order. If I had just that part, that would be. But if you put them together, you're kind of tempted to say, oh, I've got these two, but there's two separate strings and we've got these incomparable elements. So this is not a total order, because there are incomparable elements. Okay, so don't let that tempt you. Okay, so here these Hasse diagrams were already drawn for us. And the next one, we're going to look at some partial orders that are given to us as digraphs, and then turn those into Hasse diagrams that are equivalent for those partial orders. Okay, so it's usually a good idea to look first of all for the minimal elements so you know what to put on the bottom. So what are the minimal elements that we have in this particular digraph? There's only one, and it's 1. And how can you tell that it's minimal? Because there's only edges coming out of it besides this self loop. So there's only directed edges coming out and none coming in. So 1 is going to be our minimum. So that's what we would start with. We'd start with 1. Okay. And we know that in our Hasse diagram, we're going to get rid of all of these self loops. We don't need any of those. And then we're going to get rid of any edges that are there just because of transitivity. Okay, so what kinds of edges are only there to show transitivity? The one between, well, there's no edge between 4 and 6. 1 to 6, yeah, so 1 to 3, 3 to 6, I can get that from, I don't need this edge. What's the other transitive edge that's in there?
1 to 4.
Yeah, 1 to 4. So I have 1 to 2 and 2 to 4 already. I'm not going to need this one either. Okay, and so I can get rid of all those transitive edges, all of those self loops. I'll still need the 1 to 2, and 2 has to go higher than 3. There is no relationship between 2 and 3. There's no edge in there, so I can put 3 in the same level as 3, but it has to be above 1 because of that relationship. So I'll have the 1 to 3. And then when I put 4 in, that's going to have to go above 2 because it's related to 2. And there'll be an edge there. And then when I put 6 in the diagram, that's going to have to go higher than 3, and it'll also have to be higher than 2. But I can put it on the same level as 4 because it's not comparable to 4 at all. Okay, and so I need that relationship from 2 to 6, and I need that one from 3 to 6.
It's kind of convenient how that specific digraph was arranged already.
Yes, it was. And this one is not so nice. We start easy and then a little bit more challenging. Okay, so over here, again, we want to start with the minimum. So A is the minimum on this one. Okay, so notice, get rid of the self loops. It's easier to see. And A only has edges that are coming out. So A is going to go at the bottom. Okay, and then are there any edges in this one that we would be able to get rid of in the Hasse diagram just because it's only there for transitivity? Yeah, A to D, so we can get rid of that one. Okay, so A is related to B, so B is going to have to go above it. So B is going to have to come up here, and I'm going to have to put that relationship in. A is related to C, so C has to go above A. C it's incomparable to B, so it can go at the same level as B. And I'm going to have to put that relationship in. And then when I add D, well, D and B are related. D is the one that's greater. Okay, so D has to go above B. And I have to put that relationship in. Okay, so this one, you had to think a little bit more. The A is on the top there, it's on the bottom here, because it's a minimal element, because it's got all the edges coming out of it. Okay, and then in this last one, okay, that's a 1, 2, 3, 4. Sorry, it's blurry. Say, what's the minimal element in this one? 1 is. Okay. Remember, we can get rid of all these little self loops. And then this relationship here, so all these edges that are coming out the side, all of those are there solely for transitivity, right? So this 1 to 2, that 1 to 3 right there, I could get rid of that edge and I would still know 1 to 3, right? So I can get rid of this one. Same thing with the 2 to 4. I've already got 2 to 3, 3 to 4. It's implied that's 2 to 4. I can get rid of that one. That's only there for transitivity. And the 1 to 4, same thing. It's only there because I've got 1 to 2, 2 to 4, 1 to 3, 3 to 4, different ways of giving you transitivity. So this one, all I need is the 1 to 2 to 3 to 4. Okay. And so this one we can easily see as a total order. And you can kind of see it in this one too, but it's just very busy, right? And last Hasse diagram. So this one, we're just given a bunch of ordered pairs. Let's turn this one into a Hasse diagram. Okay, oh, sorry. All right, and so we know in the Hasse diagram that we're not gonna need any self loops because of the reflexive properties, right? And so we can just kind of ignore all of these, right? Just now we've just, cut down by half the number of ordered pairs that we have to look at. Okay, are there any pairs listed in here that we could get rid of because it's implied by transitivity? So AF. I don't think so. Because I'd have to have A related to something and something related to F, so AF. I don't have A related to anything else. So I can't get rid of that one. That's important. How about C to F? Okay, so we've got C to A to F. So I know I have to have C to F by transitivity. So this one implied by transitivity. So I won't have to put that one in there. Okay. And then I've got B to E. There isn't E to anything else. Like so, B to D. There isn't D to anything else. So I think that's all I can get rid of. Okay, and so what looks like a minimal element where there's nothing that's before it, that's lower than it?
E and D.
Okay, so E is not the first element in any of these. I don't think E is. But C is. So C, okay, so we've got C as a first element, and then we've got B. Okay. But we know A isn't because C is under A here. So let's start with C. Okay. So I'm going to have to go C to A. That takes care of this one. And while I'm at it, I have that A. Let's do A to F. Okay. And that takes care of this one. I'll just put X's through these so we know we don't need those ones. Okay, and so we have B to E, we have B to D, D, E, none of that appears in here anywhere. So B can go in its own separate little spot over here. But B has to be lower than E, so I'll put B to E here. And B has to be lower than D, so I'll put B to D here. So that takes care of that relationship and that relationship. And now we've accounted for all of them. And nothing extra either. We've got B to E, we've got B to D, we've got C to A, we've got A to F, and then since there's a path, an upward path from C to F, that one's implied, and then all the self loops are implied. But there's nothing extra in there that can be implied from that diagram. Okay. And this is probably a lot easier to see what the maximal and minimal elements are than trying to go through there and figure them out. So those Hasse diagrams are very convenient for drawing our partially ordered sets. Okay. All right, so that does it for partially ordered sets, and the next special kind of relationship we're looking at is equivalence relations. So remember, partially ordered sets, what three properties did they have to have? They had to be transitive, they had to be antisymmetric, and we already said that, transitive, antisymmetric, and reflexive. Those were the three things that we had to have for partially ordered sets. Okay, so equivalence relations, they are also reflexive and transitive, but this time they're symmetric instead of antisymmetric. So notice the difference. So a partially ordered set would have antisymmetric here, an equivalence relation has symmetric here. Other than that, they're both reflexive and transitive. Okay. So you know how we use this little notation for a partially ordered set? Well, we use this little tilde that looks like similar, like that's also the notation you would use for similarity. Okay, that's the notation that we use for an equivalence relation. So if you ever see this little tilde between two, you know it's a relation that's special. It's a equivalence relation, which means automatically that it's reflexive, symmetric, and transitive. Okay, and you would read that x is equivalent to y. It's related to y in an equivalence relation, so it has this kind of equivalent idea to it. All right, so let's look at an example. We have a set that contains the number 0 through 10, and we're going to define a relation R so that x is related to y if, now are you familiar with the mod operation? Okay, so that's like the percent operation in C or Java, C++ or Java, where you get the remainder. So really what this is saying is, okay, x is related to y if the remainder is the same when divided by 4. Right, that's what the mod operator does. It gives you the remainder. So when I take x mod 4, it'll tell me what the remainder is when I divide it by 4. Okay, so we have lots of things in this, but let's start with 0. So I'm going to put it. Okay, so of course 0 has the same remainder as itself. We're going to actually do the diagram. This isn't a partially ordered set, so we don't get to use a Hasse diagram. Okay, so what other numbers from this set would give us a remainder of 0 when divided by 4? So 4. So 0 is going to be related to 4. Okay. And because it's symmetric, 4 is related to 0. So those both have a remainder of 0 when divided by 4. Anything else? 8. I'm going to put this one here. So 0 and 8 both have the same remainder when divided by 4. Okay, of course, 4 has the same remainder itself, 8 has the same remainder as itself, and then 4 has the same remainder as 8, and 8 has the same remainder as 4. Okay, so that seems like all the ones that we can think of that would be related to 0, and the kind of the path we got from there. So let's go to 1. 1 is not related to any of these. 1 is related to itself. What other numbers would be related to 1? So the same remainder when divided by 4. So the remainder of 1 when you divide it by 4. 5. Okay, so 1 will be related to 5. 5 will be related to 1. Of course, 5 is going to be related to itself. What else? 9. Okay, so I'll put 9. 9 is related to itself, and then of course 9 and 1 have to have the same remainder. Okay, and that's everything that's related to 1. Okay, so moving on to 2. Okay, 2 isn't related to any of these. 2 isn't related to any of these, so 2 is going to be sort of off over here, of course related to itself. What else has a remainder of 2 when divided by 4? 6. Okay, so I'm going to have those ones. What was after 6? 10. Okay, so 6 is related to 10, 10 is related to 6, of course 10 is related to itself, and then 2 and 10 have the same remainder, so we'll have edges going back and forth between them. Okay, all right, so on to 3. 3 doesn't have the same remainder as anything that we've seen so far. 3 is over here, of course has the same remainder itself. What else has the same remainder as 3? 7. And then that's it. Okay. And so we've done 3, we've done 4, 5, 6, 7, 8, 9, 10. We've got all the numbers that were in there and what they're related to. Okay. So when we draw this diagram, what do we notice that happens? Yeah, we've got these little clumps of completely separated elements where there's no crossover. And like every connection possible is in this little clump and this little clump and this little clump and this little clump. But there's no relationships between those. Okay, so we've got these little clusters. We've got these separate clusters that are unconnected. And that's going to happen every single time. So we've got these, I'll just call them unconnected clusters of elements. Okay. And so all of these are related to each other. 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 But there's no relation between the little clumps there. Okay. And so it always kind of gets divided up like that. And those little clumps that we see are called equivalence classes. So if A is the domain of some kind of an equivalence relation, remember that equivalence relation has to be reflexive, has to be symmetric, has to be transitive. Okay. And then we've got some element A from that set. When I put the little square brackets around it, that is going to denote the set of all things that are related to A. So for example, if we went back here, if I were to look at little brackets around 0, I would list all the things that are related to 0. Okay, well that would be 0 and 4 and 8. All of those things would be in, okay, that, little square brackets around 0. That's the set of all the things that are related to X. Okay, and so that is called an equivalence class. They're basically, I can use them all, they're all equivalent to each other. They're all equivalent in some way, whatever we've decided for our relation. Okay, so if we look at our previous example, we've got that set defined the same way. How many equivalence classes do we have? 4 of them. Okay, so there's 4 of them. And what are they? Well, if I looked at 0, okay, this has exactly the same thing as the elements that are related to 4, and that's exactly as the elements that are related to 8. Those are all the same thing. So this is the set of things related to 0. Okay, I'll just write them off. So what's related to 0? Well, 0, 4, and 8 are all related to 0. What's related to 4? Well, 0 and 4 and 8 are all related to 4. What's related to 8? Well, 0 and 4 and 8 are all related. So these are all just ways of saying exactly the same set. Okay. And then if we go on to 1, well, that's the same exact elements that are related to 5. And that's exactly the same elements that are related to 9. Those are all the same thing. And then we had 2, that's the same thing as 6 and 10. And then our elements related to 3, that would be the same as 7. Okay. So we could use anything that we wanted to for the equivalence classes. We could say there's 4 equivalence classes, and we could call them, 8, bracket 8, bracket 9, bracket 10, and bracket 7. Okay. But in this context, probably not the way that we would name them. Because when we think about mod, when I divide something by 4, what are the possible remainders? I could get a remainder of 0, a remainder of 1, a remainder of 2, a remainder of 3. My remainder has to be less than what I'm divided by. So it makes way more sense, and it's more intuitive to say, okay, well, our equivalence classes, we're going to call them the class of things that have remainder 0, the class of things that have remainder 1, remainder 2, remainder 3. So we would say our equivalence classes are this one, this one, this one. So the equivalence class for 0, the equivalence class for 1, the equivalence class for 2, the equivalence class for 3. So these ones are the most representative and meaningful members in their class, so we would probably use them. Now yes, this one is the same thing as the equivalence class of 4, but in terms of the context of the problem, that's not as meaningful to us. So these are the ones we would probably choose. Okay. You guys ready to do a proof? Yeah, you are. You're ready to do a proof. Hey, how come it's not switching? Oh, there we go. All right, so we have a theorem here that tells us something about equivalence classes. So two equivalence classes are either identical, they're exactly the same thing, or they're completely disjoint. And we've already seen that on an example. So here we've seen that the equivalence class for 0 and 4 are completely identical. The equivalence class for 0 and 8 are completely identical. So these are either all completely identical, or if I pick something else, they're going to be completely disjoint. There's no overlap whatsoever. Okay, this is just one example where we can see that happening, but the theorem tells us that this always happens, no matter what the equivalent. It doesn't have to be just like the mod operator. No matter what equivalence relation we look at, this is always going to happen. Okay, so we have an equivalence relation on a set A, and X and Y are two elements in A, so they're either identical, which means if X is related to Y, then their equivalence classes are identical, or they're completely disjoint. So if they're not related, then their two equivalence classes have 0. The empty set is their only intersection. There's nothing in common. They don't intersect each other at all. So to prove this, we've got two things that we have to prove. We have to prove statement number 1 and statement number 2. Okay. So statement number 1, we'll use a direct proof for that one. I'll probably try to do half and half so we can fit it all on the spot. Okay, so the first thing that we need to prove is that if X and Y are related, then their equivalence classes have to be exactly the same. So if you think back to, I know this is a long time ago, but for two sets to be equal, okay, the way that we define two sets to be equal is that for every element that's in the first set, it also has to appear in the second set. So if I can just pick an arbitrary element in this first set, set X, and show that any arbitrary element in the first one has to appear in the second one, then I'll show that they're equal. Because that's the definition of equality, that for all elements of the first set, it's an element of the second set. Okay, so that's where we're going. Okay, so we have, should we say that this will be a direct proof? That will help you keep track of what we're doing. Okay, so we already have this. We have X and Y are in A. That's part of one of the things we know. And we have that X is related to Y. Okay, so that's our hypothesis there. So, and this is, our given as well. And now what we need to prove is our conclusion, that these two sets are exactly the same thing. Okay, so let the element Z from A be an arbitrary element such that Z is in the first set. Okay, so I know I'm just going to pick some random element from the first set. There's nothing special about it. It's just a random element. All I know is that it's in this set. Now, if I can show and it's also in the second set, then I know they're equal, because whenever I pick an arbitrary element from the first set, it's in the second set, they must be the same set. Okay, so that's my goal, was to show that Z, well, let's write that, okay. We will show that Z has to be in this other set as well, the second set as well. And if we can show that, that'll be enough to say that they're equal. Okay, so if Z is in X, that means that Z is related to X, okay, since it's in that set. Okay, the only way it gets to be in that set is if it's related to X, right? So we have that. Okay. And so notice what we have. We've got Z is related to X because it's in this set. And part of our hypothesis was that X is related to Y. And what are the properties of an equivalence relation? They are, what three things? Symmetric, transitive, and reflexive. Okay, and so does it look like, let me just put a different color under here. If I know these two things, that I could apply any of those properties to help me make another conclusion. Yeah, we can apply the transitive property, because I've got Z is related to X, X is related to Y, so what can I conclude because it's transitive? Yeah, so Z has to be related to Y because because that relationship is transitive. Okay. And if Z is related to Y, does that mean that it's in the equivalence class of Y? Yes. So Z has to be in the equivalence class of Y. Okay. And that's exactly what we are. Okay. Okay. So in other words, we know that this set X has to be the same as this one Y. Because whenever I find an element that's in X, it also has to be in the equivalence class of Y. Okay, so that takes care of number one. Number two says it is not the case that X is related to Y. Okay, so whenever you see it is not the case, okay, probably direct proof is not the same way that we want to go. Any ideas what kind of? So maybe contrapositive or maybe contradiction, right? So one of those two. We'll do a proof by contradiction. Okay, so for the second one, we're going to use a proof by contradiction. Okay. So we know that X and Y are in A. Okay. And we've got our hypothesis here. Okay, so it is not the case that X is related to Y. Okay. So in a proof by contradiction, we're going to assume the opposite of what we're trying to prove and then show that we get to some kind of contradiction when we assume the opposite. So we're going to assume. And then what's the opposite of the intersection is the empty set? That it's not the empty set. So we're going to assume that when I take the equivalence class of X and intersect it with the equivalence class of Y, that I'm not going to get the empty set. Okay. So if it's not the empty set, that means there has to be at least one element in there, because the intersection isn't empty. Okay. So then there exists some element Z such that Z is in X and it also has to be in Y. The only way I can get a non-empty intersection is if there's at least one element that's in both of the sets. Okay. All right, well, if Z is in this first set. The only way it got in there is by being related to it. Okay, so we know then that z has to be related to x. And the only way that z got into this equivalence class is that it had to be related to it. So z has to be related to y. Okay. Now I'm trying to arrive at a contradiction. Okay, and so notice what I had up here, that it's not the case that x is related to y. So if I could somehow show that x was related to y, it would contradict this, and I would have the contradiction that I needed. Okay, so it seems like transitivity, yes, but I have to do a little bit of tweaking, because in order to use transitivity, I have to have x is related to something, and that something is related to y. Right now, I don't have x is related to something. But I do have z is related to x. Could I rewrite that as x is related to z?
Yes,
Why? Yes, because it's symmetric. Okay. So I'm going to put, but x is related to z because this relationship is symmetric. Okay, and now I have x is related to z, z is related to y, and so now I can conclude what? So x has to be related to y, and that's because the relationship is what? It's transitive. Good. Okay. So now I have that x is related to y, but up here I said it is not the case that x is related to y. There's our contradiction. So this contradicts the fact that, okay, I'm just going to put not x related to y. That's what this is said, right? Okay. So our assumption that we made up here must be false, right? And it must really be the case that the intersection of those two things actually is the empty set. It's always good to review a little bit of direct proofs and proofs by contradiction, right? Always. It's always good. Okay. All right, so now, since we've proved it, we know that it's true, that we're going to have these equivalence classes, and that we're going to get these things that there. If I've got one element in the equivalence class, its equivalence class is exactly the same thing, and there's never any overlap between these. And where have we seen this kind of situation arise before? Where we have like a set and it gets divided up into these non-empty subsets that are pairwise disjoint. Oh, we saw this a long time ago when we talked about partitions. And so these equivalence classes partition that domain that we have the relation defined on. Okay, so recall we have a partition. We did this way back in chapter whatever it was, 2, I think. So if we have these non-empty subsets and they're pairwise disjoint and their union is A, that's a partition, and that's exactly what we get with these equivalence classes. They're disjoint. We just proved that they're disjoint. And when you put them all together, you get the whole set. Okay, and so going back to this power set example, but a new relation, but again, thinking about the power set. Let's say we have a relation and we define it as two elements of the power set are going to be related if, and then what does this notation mean? So realize that A is a set and B is a set. When I put these little, they're what?
They have the same number for them.
Yeah, they're cardinality. So the cardinality, so remember, these little bars here, this means the cardinality of B. Okay, so all of the elements in this are going to be sets. Okay, so this is a set, and the two sets are related if they have exactly the same cardinality. Okay, and so let's think about what is the what's the smallest set that you can think of in the power set of 0, 1, 2? the null set, the empty set. Okay. Okay, so now I want to think of every single thing that's related to the empty set. What is in there? What else? What other subsets would have a cardinality of 0 like this one? Okay. Are there any other subsets that have a cardinality of 0? No, right? There's not. So it's in a little class all by itself. It's lonely, but it's there. All right. And then the next maybe smallest set I can think of is the set that just has one element in it. Okay. All right. Are there any other elements that would also only have one element that would be in that same equivalence class? Just one all by itself and two all by itself. Okay, those all have a cardinality of 1. So this has a cardinality of 1, this has a cardinality of 1, this has a cardinality of 1. They're all the same. Okay, and we'll just have to pick one representative set, but that's the same. All three of those are the same thing. Okay, what's another subset that's going to give us a different partition? Like 0 and 1. Okay, so that has a cardinality of 2. What other subsets do we have with a cardinality of 2? 1, 2, and 0, 2. I heard those. Okay, so I've got 1, 2, and I've got 0, 2. Those would both have cardinality of 2. Any more equivalence classes? How many subsets should we have? We should have 8. Let's see how many we've accounted for. 1, 2, 3, 4, 5, 6, 7. What are we missing? All 3 of them. And that has a cardinality of 3, so it's not going to be in any of these equivalence classes. It has its class all of its own. Okay, so this would be the sets of cardinality. This is sets cardinality 0. This is the sets with cardinality 1. This is the sets with cardinality 2. And this is the sets with cardinality 3. Okay, so we've got 4 different equivalence classes, and we just need to pick representative subsets, so we could probably just pick these 4. Okay, so these are our 4 equivalence classes. Yeah, sorry. So these 4, so I just need to pick a representative set from the 4 classes. I'm just going to pick the first one. Okay, so but those are our 4 equivalence classes. Notice they're all disjoint. Okay, they're non-empty, and they're union. When you put it together, you're going to get all 8 of the subsets. Okay. All right, and one last example. Let's say we've got this set S, and it's going to take either 0, 1, and make strings of length 4, so bit strings of length 4. So it's got 4 bits in it of 0s and 1s. And we're going to define the relationship that A and B, so the two 4-bit strings, are related if we can take A, and it can be obtained by reordering the bits of B. Okay, so how many bit strings do we have? More than 8. So I've got 4 slots. How many choices do I have here? 2. Choices here. Choices here. 2. Okay, so what do I do with all those numbers? Yeah, so I got to multiply them. There's like 16 choices, right? So I've got 16 different bit strings. Okay, so I don't want to write them all out, but I should be able to come up with, okay, so what is a bit string that, like, let's just pick the first one, okay? So no matter how I reorder it, I can get something. So let's think about the bit string 0, 0, 0, 0. Okay. So no matter how I reorder that, I'm going to get 0, 0, 0. Is that equivalent to any other bit strings? Are there any other bit strings that I could shuffle around and get this? No. Okay, so this is going, so I can think of this one as being the strings with no ones. Okay. What do you think would be the next representative string that I could shuffle around? I could do all ones. Okay, let's not do that one next. How about 1, 1? Okay, so if I just want 1, 1 in it, okay, so let's do it like this, 0, 0, 0, 1. Okay, so this will be all the strings with 1, 1. Okay. And so this is going to include a whole bunch of them. This will give me 0, 0, 1, 0, and 0, 1, 0, 0, and 1, 0, 0, 0. They're all included in that set. Any way I can shuffle that around and just get 1, 1. They're all included in there. Okay, what's my next representative string? Yeah, 2 of each, so 0, 0, 1, 1. Let's just make it like that. Okay, so it'll be strings with 2 ones. Okay, and so there's a bunch of them in there, right? So I could have 1, 1, 0, 0, 1, 0, 1, 0, 1, 0, 0, 1, 1, 0, 0, 1. Shuffle them. So anything that has 2 ones in it. The next one, 3 ones. Okay, so this will be strings with 3 ones. And then our last class would be 1, 1, 1, 1. So that would be all the strings with 4 ones. Okay. And that should cover everything, right? There's not going to be any overlap between these. Okay? There's not any string that's going to show up in this set that would be in any other set, because this one only has 1. This one has 0. This one has 2. There can't be any overlap. Okay, and I've accounted for every single thing, right? There isn't anything in here that I haven't accounted for. I've accounted for 0 all the way up to 4 ones, and since I've got 4 bits, that's the bit. I have to be able to go from 0 to 4. So I've accounted for every string. So I've got these 5 equivalence classes. And I don't have to write out every single element, but I know that that covers everything. Okay, and it will partition my set of bit strings, and I'll cover everything.
So how
Yes.
does this work again? I'm kind of confused.
So I haven't written out everything that's in this set because there's too many of them, right? We don't have to write down all 16 of them. But I know that what's in this set, this is a set, and that set contains every string that can be reordered from this bit. So every permutation of these bits.
Oh, so you can put it in order.
Yeah, so I could make it 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0. It's like any order, okay, all of those strings are going to be in this set. But the caveat is that there's only going to be 1, 1. So everything with 1, 1, all those strings are going to be in this set. All the ones with 2 ones are going to be in this set. 3 ones, 4 ones. Okay. Now these two, these are the only ones there are. It's the other ones that have lots of strings in them. These ones they're loaders. Okay. All right, so that does it for chapter 6. We're going to start chapter 7 on functions next time. And so before class on Thursday, you need to finish up 6.3 and 6.4 in Zybooks. I'll post that on iLearn, but 6.4 and 6.3 and 6.4, so on partially ordered sets and equivalence relations, should be finished by Thursday. And we will look at functions on Thursday. And if you have any questions about your bonus things, just email me.